Dear students, welcome back to another video lecture on the course Signals and Systems with course code 18EC45. In the previous video lecture, we understood the relationship between impulse response and four of the system properties. For an LTI system to be memoryless system, its impulse response should be a constant, represented by the form. For discrete LTI system, impulse response h of n should be of the form c delta n, and for continuous LTI system, impulse response h of t should be of the form c delta t. Then only LTI system will be memoryless system. For LTI system to be causal system, its impulse response should be of the form. For discrete LTI system, h of n should be equal to 0 for n less than 0. For continuous LTI system, h of tau should be equal to 0 for tau less than 0, meaning for causal LTI system, impulse response should be equal to 0 for negative time. Then only LTI system will be causal. For system to be stable, for discrete LTI system to be stable, its impulse response should be absolutely summable. For continuous LTI system to be stable, its impulse response should be absolutely integrable. Impulse response for a stable LTI system should be of finite value. And for LTI system to be invertible, the convolution between the impulse response of the original system and the impulse response of the inverse system should be a delta function, because delta function is an identity sequence for convolution. Therefore, convolution between delta function and the input signal, input to the original system, input signal will be resulting into an input signal itself. In today's video lecture, we'll solve some problems to understand the relationship between the impulse response and the system properties that I have briefed just now. Later, we'll understand what is step response and how do we obtain step response from impulse response, and solve some problems to obtain step response from the impulse response. So the first problem we'll consider is investigate the causality and stability of the following systems. A discrete time system is defined by the impulse response h of n equals to 2 to the power n u of n minus 1. Now this impulse response is an exponential form. The nature of this impulse response is exponential, which will be starting from n equals to plus 1, and it will be present till infinity. That means impulse response is 0 for n less than 1, and the condition for causal LTI system is impulse response should be 0 for negative time, that is n less than 0. Therefore, the system under investigation is a causal system. Now to check the stability, we'll have to verify if the given impulse response is of finite value or it is absolutely summable. Now to verify this, we'll consider an variable s and use the expression summation n minus infinity to plus infinity magnitude of h of n. Now magnitude of h of n is 2 to the power n u of n minus 1. Now because of this u of n minus 1, the lower limit will be 1 and upper limit will be infinity, because it is an unit step function starting from 1 and it will be present till infinity of 2 to the power n. Now this is the geometric series on 2. For every iteration, 2 will be added. For n equals to 1, it will be 2. For n equals to 2, it will be 4. For n equals to 3, it will be 8. Likewise, till infinity. If we add all of those values, it will be equal to infinity, because last value is infinity. Because impulse response value is infinity, the system under investigation is an unstable system because it is not absolutely summable. The second system we'll consider is, the second system has an impulse response defined as alpha to the power n u of n. Again, this is an exponential signal. Now this impulse response, because of u of n present, will be having the values from n equal to 0 to infinity only. Again, impulse response is 0 for n less than 0. Therefore, the system is causal. Now to check the absolute summability, we'll use alpha to the power n u of n in the summation, and because of u of n, lower limit will be 0 and upper limit will be infinity. If we use the standard geometric form, it will be 1 divided by 1 minus alpha. Now this system is conditionally stable. And what is that condition? When s will be a finite value, whenever alpha value, magnitude of alpha is less than 1, only then 1 divided by 1 minus alpha will be a finite value. Therefore, the system defined by the impulse response h of n equals to alpha to the power n u of n will be stable if and only if magnitude value of alpha is less than 1, not equal to, sorry. If magnitude value of alpha is less than 1, then only the system will be stable. System is defined by an impulse response h of t equals to e to the power minus 2 of magnitude of t. Now this is a continuous time system's impulse response, and if you look at the nature of this impulse response, it's a two-sided function. From minus infinity to 0, it's an exponentially growing signal defined by e to the power 2t u of minus t, and from 0 to infinity it is an exponentially decaying signal defined by e to the power minus 2t u of t. And the nature of this impulse response has been drawn on the right side. Now, is it a memoryless system? Yes, system is not a memoryless system because impulse response is not of constant form. Therefore, it is not a memoryless system, it is a memory system. Now, is it a causal system? No, it is a non-causal system because impulse response is non-zero between minus infinity and 0, that is for t less than 0. It is exponentially growing signal. Because it is non-zero for t less than 0, the system is non-causal. To check absolute integrability for the given impulse response, we'll use the expression s equals to integration minus infinity to plus infinity magnitude of h of t integration with respect to time. Now because the function exists from minus infinity to plus infinity, we'll divide the integration for negative time and positive time. So integration minus infinity to 0, and within that time exponential is e to the power 2t dt plus integration 0 to infinity e to the power minus 2t dt. If we simplify this, we'll get half plus half, which is equal to 1. So the value of the impulse response is 1, which is a finite value. Therefore, the system is bounded input, bounded output, stable. That means impulse response is of finite value. If we apply bounded input, then if the system produces bounded output, then the system is stable system. And the fourth system that we'll consider has the impulse response h of t equals to e to the power 2t u of t minus 1. Now because of this u of t minus 1, this continuous time exponential impulse response will be present from 1 to infinity as shown in the figure on the right side. And at t equals to 1, the value of this exponential will be e to the power 2 or e square. Now, is it a memoryless system? It is not a memoryless system because again, the impulse response is not of the form c delta t. It is not a constant. Therefore, it is not a memoryless system. It is a memory system. Now, is it a causal system? Yes, it is a causal system because impulse response is starting from t equals to 1. That means impulse response is 0 for t less than 1. Therefore, it is a causal system. And if we use the expression s equal to integration minus infinity to plus infinity magnitude of h of t dt, if we use the function, then the lower limit will be 1 and upper limit will be infinity, because the function is starting from 1 and within that period the exponential is defined as e to the power 2t dt. If we integrate and substitute the limits, the value we'll get is infinity. Because the value of the impulse response is infinity, the system is unstable system. Next topic is step response. Now, step response, just like impulse response, is the output of linear time invariant system when unit step function is applied as an input to it. We all know the definition of impulse response. Impulse response is the output of a system, output of LTI system, linear time invariant system, when unit impulse function is applied as an input to it. Likewise, step response is also an output of LTI system itself, but the input to that LTI system will be unit step function this time. Now, when we say step function is an output of LTI system, then that LTI system will be characterized by the impulse response. Now, what is the relationship between impulse response and step response? We'll go through in a moment. Now, we'll use unit step function as an input signal to understand how the system behaves for sudden change in the input. Now, let us consider a system, LTI system, whose impulse response is defined as h of n, and to this LTI system will apply unit step function u of n as an input. So output from this LTI system will be denoted by s of n, which has to be an unit step function, unit step response. So unit step response will be denoted by s of n. Now this has to be an unit step response because the unit is unit step function. Therefore, s of n will be represented as u of n convolution with h of n, because s of n is the output of LTI system, and output of LTI system will be convolution between input and impulse response. And also, because of the commutative property, s of n can also be written as h of n convolution with u of n. H of n is the impulse response and u of n step function is the input. Writing the convolution summation for the above LTI system, s of n will be equals to summation k minus infinity to plus infinity h of k u of n minus k. Now u of n minus k is reflected and shifted version of the unit step function, which is defined as, it will be having only two values, either it will be equal to 1 or 0. Now the question is, when will it be equal to 1 and when will it will be equal to 0. So according to the standard definition of unit step function, all unit step functions will be 1 for independent variable greater than or equal to 0, and this case the function is n minus 1. So therefore u of n minus k will be equal to 1 for n minus k greater than or equal to 0. If you send this minus k to the other side, then the condition will be k less than or equal to n, and it will be 0 for k greater than n. So u of n minus k will be 1 for k less than or equal to n, and it will be 0 for k greater than n. Now using this result in the convolution summation, we'll get s of n will be equals to summation k, lower limit will be minus infinity itself, but the upper limit will be n, because unit step function u of n minus k will be 1 for k less than or equal to n only. For k greater than n it will be 0. So entire summation will be 0. So lower limit will be minus infinity and upper limit will be n of h of k. This means step response, s of n is step response, h of k is impulse response. Step response, s of n is an running sum of the impulse response, or step response S of n will be obtained by accumulating or adding all the values of the impulse response till k is equal to n. Similarly, for continuous linear time invariant systems, step response will be denoted by S of t, and this step response is a running integral of the impulse response. So S of t will be equals to integration minus infinity to t h of tau d tau, where S of t is the step response and h of tau is the impulse response. Now if we invert these relations, then we'll be able to obtain impulse response from the step response. So in case of discrete time linear time invariant system, impulse response will be the first difference of the step response, denoted by h of n equals to s of n minus s of n minus 1. And in case of continuous LTI systems, impulse response will be the first derivative of the step response, given by h of t equal to ds of t divided by dt. So for discrete time, impulse response is first difference of the step response, and for continuous times case, impulse response is first derivative of the step response. Now in the following section, we'll solve some problems to obtain step response from the impulse response. And the first problem we'll consider is evaluate the step response of an LTI system represented by the impulse response h of n equals to half to the power n u of n. And the step response, because it is an running sum, it is defined as s of n equals to summation k minus infinity to n h of k. And the impulse response is an exponential function, but it is defined only for n between 0 and infinity. Impulse response is 0 for negative values of n. Therefore, for n less than 0, step response will be equal to 0, because impulse response h of n is present only for positive values of n. And for n greater than or equal to 0, step response will be redefined as summation k equals to 0 to n half to the power k. If we use the standard geometric series, it will be half to the power lower limit minus half to the power upper limit plus 1 divided by 1 minus half. If we simplify this, we'll get step response as half minus half to the power n. Next problem is obtain the step response of the system defined by the impulse response h of n equals to delta n plus delta n minus 1. Now this impulse response has only two samples defined at n equals to 0 and n equals to 1, whose amplitude is 1. And the nature of this impulse response has been drawn on the right side. Step response s of n will be equals to summation k minus infinity to n h of k. We already know that. And this step response s of n is 0 for n less than 0, because there are no samples present. Impulse response exists at only two values of n, that is at 0 and 1. Therefore, for n less than 0, step response is equal to 0. For n equal to 0, there is one sample of the impulse response. Therefore, step response s of 0 will be equal to 1. And for all the values of n greater than or equal to 1, we'll be having two samples in the impulse response at n equals to 0 and at n equals to 1. Therefore, the step response will be addition of both those samples. 1 plus 1 equals to 2. Therefore, step response s of n will be having three values. It will be 0 for n less than 0, it will be 1 for n equal to 0, and it will be 2 for n greater than or equal to 1. For any value of n greater than or equal to 1, we'll be having two values in the impulse response, and step response is the running sum, that is, all of the impulse response samples have to be added to obtain the step response. All the samples are to be added where we'll be evaluating for that value of n. All the samples till that value of n are to be added together. Therefore, it will be 0 for n less than 0, it will be 1 for n equal to 0, and it will be 2 for n greater than or equal to 1. Statement of the next problem is, obtain the step response of the system continuous linear time invariant system whose impulse response is defined as h of t equals to e to the power minus magnitude of t. Now, because of this magnitude, t will be both positive as well as negative, and the nature of this impulse response has been drawn on the right hand side. H of t will be a two-sided function now. It will be an exponentially growing signal between minus infinity and 0, where it will be defined as e to the power t u of minus t, and it will be an exponentially decaying signal between 0 and infinity, where it is defined as e to the power minus t u of t. If we use the condition of absolute integrability, then s of t will be defined as integration minus infinity to t h of tau d tau. For t less than 0, s of t will be e to the power tau d tau. If we integrate for the limits minus infinity and t, we'll get the value as e to the power t. And for t greater than or equal to 0, both side functions will be considered. So integration will be divided between both the values. Integration minus infinity to 0 e to the power tau d tau plus integration 0 to t e to the power minus tau d tau. If we simplify this, then the step response will be 2 minus e to the power minus t. Therefore, for the given system, step response is e to the power t for t less than 0, and step response is 2 minus e to the power minus t for t greater than or equal to 0. And the statement for the last problem of the day is, obtain the step response of impulse response h of t equals to t square u of t. The impulse response is square of the ramp function, but it will be existing from 0 to infinity only because of this u of t. So using the step response expression, s of t equals to integration minus infinity to t h of tau d tau. For t less than 0, step response will be equal to 0 because impulse response is 0. There is nothing to integrate. For t greater than 0, s of t will be equal to integration 0 to t tau square d tau. If we integrate and use the limits, then s of t, the step response will be equals to t cube divided by 3. Therefore, step response s of t is 0 for t less than 0 and t cube divided by 3 for t greater than 0. So these were the concepts for the day. I hope all of you understood all the concepts that we covered today. If you have any doubts, you can contact me. Thank you all.